Hi, class. In this section, we want to talk about comparison tests for series. All right, so what is the idea here? So in the comparison test, the idea is to compare a given series to a series that is known to be convergent or divergent. All right, so for instance, look at this. Let's look at this series. So the summation n is equal 1 to infinity of 1 divided by 2n plus 2 to the nth power plus 1. Right, this kind of reminds us of the series, the summation n is equal 1 to infinity of 1 over 2 to the n, which we know is a geometric series with a is equal to 1/2 and r is equal to 1/2, and is therefore convergent. All right, because the series, all right, the one we have up here, 1, is similar to a convergent series, we have a feeling that it too must be convergent. So indeed it is. So we can look at this inequality right here. So we know that 1 divided by 2n plus 1 is less than 1 divided by 2n, obviously. Shows that our given series 1 has smaller terms than those of the geometric series, and therefore all its partial sums are also smaller than 1, all right, which is the sum of a geometric series. This means that its partial sums form a bounded increasing sequence, which is convergent. It also follows that the sum of this series has to be less than the sum of the geometric series, so it has to be less than 1. All right, similar reasoning can be used to prove the following test, which applies only to series whose terms are positive. That's important. The first part says if we have a series whose terms are smaller than those of a known convergent series, then our series is actually convergent. The second part says that if we start with a series whose terms are larger than those of a known divergent series, then it too is divergent. So here's the comparison test. Suppose you have the series summation a sub n and summation b sub n, all right, our series of positive terms. If b sub n is convergent and a sub n is less than b sub n for all n, then that other series, all right, summation a sub n is also convergent. If the summation b sub n is divergent, and we know a sub n is greater than or equal to b sub n for all n, then it makes sense then that the series summation a sub n is also divergent. All right, and using the comparison test, we must of course have some known series summation b sub n for the purpose of comparison. So most of the time, trust me, we're going to use these series, the p series, which we saw as the summation 1 over n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1. In a geometric series, the summation a r raised to the n minus 1 power converges if the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than 1. So we're going to try to take some of our given series and relate them back to p series and geometric series. All right, so let's look at this one. Determine whether this series converges or diverges. All right, so if you look at it, it's like, where do I even begin with this one? Well, you want to start by looking maybe just at this first term here and ignore the rest of this stuff right here. All right, so for large n, the dominant term is the denominator 2 to the n squared power, right? So we compare the given series with this series, knock off all this other stuff here, the summation 5 divided by 2n squared. So observe that this holds because the left side has a bigger denominator. All right, so you can kind of see where we're going. Now we want to look at and see if this series right here is convergent or divergent, right? Obviously, because this series is less than, we're going to show that this series here is convergent. All right, so in the notation of the comparison test, a sub n is the left side and b sub n is the right side. All right, so we know that this, all right, if I look at this series, I can factor out the 5/2 and I'm left with just this. Well, we know that this series, the summation n is equal 1 to infinity of 1 over n squared, is convergent, right? Because it's a constant right here times a p series with the p, the exponent being greater than 1. So it converges. So I took this crazy series right here and I just related it back to a p series. That's all I did. All right, so therefore this series is convergent by the first part of that comparison test. Notice how I'm not saying what it converges to, I'm just saying that it's convergent. All right, so although this condition, these two conditions in the comparison test is given for all n, we need to verify only if it holds for n greater than or equal to capital N, where n is some fixed integer. because the convergence of a series is not affected by a finite number of terms. And the terms of a series being tested must be smaller than those of the convergent series or larger than those of the divergent series. So if the terms are larger than the terms of the convergent series or smaller than the divergent series, then obviously this comparison test just doesn't apply. All right, let's look at this one. Consider, for instance, this series right here. All right, we could say that this inequality holds right here. Obviously, that this series or this is greater than this. All right, this is useless as far as the comparison test is concerned because the summation of b sub n is equal to the summation of 1/2 b to the m is convergent. And what we see here then is that a sub n is greater than b sub n. So if this is convergent, but this is greater than, it does not imply that this is also convergent, right? The inequality would have to be flipped for that to be so. So if the bottom series here is convergent, it doesn't imply that the top one is. All right, nonetheless, we still have this feeling that this series here ought to be convergent because it's very similar to the geometric series that's listed right there. In such cases, the following test can be used, right? And this is called the limit comparison test. Suppose that the series a sub n and b sub n are series with positive terms if the limit as n goes to infinity of a sub n divided by b sub n is equal to some constant, right, where c is a finite number and is greater than 0. Either both series converge or both series diverge. So if we know that this series converges, if we look at the limit test and it's equal to some number, since this one converges, the other one has to converge. All right, so let's test this series for convergence or divergence. So we use this limit comparison test. Here's my a sub n, here's my b sub n. We know b sub n converges. So when you look at the limit, all right, we have the following here. And so as n goes to infinity, all right, I'm going to simplify it to get this. So as n goes to infinity, it looks like, as I go through this, all right, this is great. This limit obviously here just equals 1, which is greater than 0. All right, since a limit exists and the summation 1 divided by 2 to the n power is a convergent geometric series, it follows that the given series converges by this limit comparison test.